Imagine your YouTube. Someone lands on the home page, and you have a fraction of a second to pick a few videos out of billions. You'd love to run a powerful model on every single query and video pair to score the match, but that math is completely impossible in real time. The two-tower model is the clever architecture that makes it possible anyway, and the same shape powers modern search, recommendation, and retrieval systems everywhere. Let's see how it sidesteps that impossible computation. The whole design hinges on splitting one hard problem into two halves that only meet at the very end. Follow a request through it. The query tower comes first. It's a neural network whose only job is to take the user or their search and squeeze it down into a single embedding, a point in some high-dimensional space that captures what this person is looking for right now. On the other side sits the item tower, a completely separate network that encodes each candidate video or product into an embedding in that exact same space. Two different networks, but they're trained to speak one shared geometric language. Here's the move that changes everything. Because the item tower doesn't depend on the query, we can run ahead of time on every item and store all those embeddings in a vector index. That heavy work happens offline, long before anyone shows up. So it's serving time. The expensive per pair scoring evaporates. We encode the query once, then do a fast approximate nearest neighbor search over the pre-computed item vectors. An impossible computation becomes a simple lookup in milliseconds, and that single trick is what lets these systems sift billions of candidates before you finish blinking. It's worth pausing on exactly what problem this solves, because the contrast is stark. The obvious approach is to feed every query and item together into one big model and let it score the match directly. That's accurate, but it's hopeless at scale. Millions of candidates times every incoming query means millions of expensive model runs per request. You simply cannot serve that. The tower design refuses to look at pairs together. Each side is encoded on its own, and they only touch through a cheap similarity at the end. That separation is precisely what lets you pre-compute one side and turn scoring into a vector search you can actually run live. You trade a little accuracy for an enormous gain in speed, and at candidate generation scale, that trade is absolutely worth it. Let's crystallize the three ideas that make this architecture so widely used. Separate encoders sharing a space is the foundation. The query tower and the item tower are distinct networks, yet they map their very different inputs into one common embedding space. So, a simple dot product between them actually means something. Without that shared geometry, comparing a user to a video would be like comparing two numbers in different currencies. Pre-computing item embeddings is where the speed comes from. Since items don't change with the query, their vectors are built once, indexed, and reused, which converts a per-pair nightmare into a fast nearest neighbor lookup at request time. Training so matches score high ties it together. The model learns to pull real query and item pairs close in that space while pushing mismatches apart, often using other items in the batch as easy negatives, and that's the same recipe behind DPR and clip. Let's wrap with the 4 points to carry away. The architecture uses two separate encoders, one for the query and one for items, mapping both into the same embedding space. The towers meet only at the end, through a cheap similarity like a dot product between their embeddings. Item embeddings are pre-computed and indexed, so serving is a fast nearest neighbor search instead of scoring every pair. Trained so real matches score high, it underpins retrieval from YouTube to semantic search, sharing its shape with DPR and clip. If you like these architectures made clear, Standarity.com has plenty more waiting for you. Catch you in the next one.